So yes, we're going to be finishing up. We're going to be working on section 5.1. Lots of things that you need to take a look at today. We need to start off by talking about what an instant is. We use the word instant all the time, but understand that an instant refers to what is happening right at that moment. So at an instant, but you don't say this happened for an instant. Like there's no measurable amount of time that is an instant. So when we begin to use the word instant or instantaneous, that's what's happening at that moment. But that does not have an interval involved in it. And that's going to be important for your calculation purposes. For those that are heading in the calculus direction, what that means is that you can sometimes find a value that approaches a certain value. For those of you that are familiar with the word limits, those that are going into calculus, or you're touching on some things in calculus, it has to do with this. Sometimes things can happen and you don't have a duration that you can look at, but you can still figure out what's happening at that time. It has no duration. What I just said, some of the things I'll bring down, I've just actually said, but so you're not writing too much all at once. And there is no answer to the question, how long is an instant? It is just a time, at that time something is happening. And the type, yes?
So when that question is asked, how long is an instant, there's no answer?
Right, so there's no answer to that question. You can't say an instant is 0.0005 seconds. Okay, there is no duration. There's no how long when you're talking about an instant. And then finally, when you have a position time graph, we call it a DT graph. D standing for position, T standing for time. It shows the location of an object at different instances in time. And yesterday we had gone over on the board where we had all of these different, like here's where this is at a certain time, and then we were able to plot those points, and the position time just shows where it is and when it's there at that particular instant in time. Okay, so hopefully that makes some good sense to you. Good. D is position and T is time. So position versus time. Yes.
Is that the same graph as the one that we did yesterday, or is this a different graph?
Yeah, actually, and I can kind of look at a very rough version of the graph we did yesterday. Over here, position versus time. Where is something at what particular time? And it related to this graph right over here. We had a person that was walking up and down this street, going west to east or east to west, and passing by 6th Street, and where they were was plotted on this graph when we were taking a look at that. It's actually already up online, so you can take a look at that in the notes that are online, so that's good. All right. And here we go. We went through this one, went through this one, went through this one. Okay, so we want to answer these questions right here. First thing, you can take your notes any way that you want, so you don't have to write everything word for word. But just I want to have this discussion so that you know what these things actually are referring to. Because we looked at that graph. How does a DT graph appear if an object is in constant forward motion? Usually forward, because usually we set up our coordinate system so that forward is in the positive direction. So when you have a DT graph, position this axis, time this axis, and it's moving forward, what is that going to look like? Constant speed, but what does constant speed look like?
Same distance between each.
Same distance in each time interval. So would that be a curvy line or would it be a straight line? It's going to be a straight line, and it's going to be tilted up and to the right. So it's going to be a positive slope up and to the right, and it'll be a straight line. If it was a curved line, that would mean that maybe it's getting faster or maybe it's getting slower. But if it's a nice straight line, that means that it's going to be having constant positive motion, because your rise over run is going to be positive, and we will take a look at quite a lot having to do with graphs as we go through the rest of the course. Okay, so how does a DT graph appear if the object is in constant negative motion? Straight, straight and negative slope. So a straight negative slope, and really if you're just taking notes, you would say a straight negative slope means constant negative motion. I've got it formed as a question, so you can write it down however it makes sense to you so you can understand later. Yes?
Will an arrow on that straight line tell us if it's negative or positive?
An arrow on the straight line wouldn't really tell you negative or positive. It's completely by the slope.
Okay.
Okay, an arrow would just mean goes on forever in that direction. And a lot of times, actually, in the DT type of graphs, we do have a beginning and an end to motion. So it may not be as it goes on forever like we do in math class a lot. So a DT graph, how does it appear when the object is at rest? And we ran across that when we were talking about yesterday's graph. What was happening when the object was high street? Straight, no slope, zero slope, line. Straight horizontal line, slope equals 0. It was hanging out on 6th Street. I was thinking of one of your homework questions. So just straight line, not moving. The thing is that it is actually a straight line, but since time is going on, but that object is at rest even though time continues to go on, so it actually flattens out on the graph. So since from what we were talking about yesterday. Okay. So you do need to make sure that you know positive slope up and to the right means positive constant motion. Down and to the right, negative slope, and with negative motion backwards. Evened out like this would be a slope of 0. And a vertical line actually is impossible. On a DT graph, what would a vertical line suggest?
Time is not real.
Yeah, time is not real because it would indicate that something was at multiple locations at the same time. And you don't really have that. You can't have that. Something has to be just in one place. We're not in some kind of a comic book world or anything like that. Impossible. Yes. Not possible. Okay, so another word for constant speed is uniform motion. Okay, or constant velocity. Constant speed is not quite what constant velocity is. Constant velocity puts direction also into the picture. So uniform motion is specifically constant velocity, where something is moving in equal displacements during successive equal time intervals. Anybody remember what the difference is between displacement and distance? Okay, well, what's distance? How far? And what makes displacement different? How far and not the time, but how far and what? Position, not necessarily, because displacement is a change in position, but it's how far and in what starts with a D.
Direction.
Direction, I heard it, yes. So how far and in what direction for displacement? So equal displacements, same distance and in the same direction over successive equal time intervals. So it's going at a constant speed and constant velocity. Constant speed could be in a curve, but constant velocity just in a straight line. The direction and the distance, the direction and the distance being the same. So back to remembering with your math, slope is rise over run. You should have had that so many times you're kind of sick of hearing it. Okay. Hmm? Okay.
Let's get a piece of scrap paper.
Mm-hmm. Okay, so the rise over the run is the how far up, how far over. So just so you remember from your algebra days, y2 minus y1 over x2 minus x1, that should be completely very, very, very old news, okay, with the slopes. And so for a dt graph, its position this way and its time this way. So that would mean that the slope on the dt graph isn't the change in y's over the change in x's. It's the change in what? Change in position over change in time. So change in position over change in time. It should look familiar because we did throw that equation out quickly at the beginning, but right now we're taking time to really, really like pull it apart, relate it completely to your math, and do problems is where we're headed for. Before we were just getting some baseline information, but now we're going to be able to do some more work with it. And if you remember, change in was a delta, so delta D over delta T. And that would give us your average velocity. I'm just adding little bits. And that bar over top means average. So our average velocity is the change in position divided by the change in time. Average velocity. And just as a little side note, as long as there's no change in how fast it's going, and as long as there's no change in velocity and its motion is uniform, then the average velocity equals the actual velocity. If the velocity is changing, which is what happens in many, many situations, most situations. So if the velocity is changing, then the average velocity will be different than the actual velocity or how fast it's going at any particular given time. So we have all that going on. I want us to take a look at a graph. So I've got one prepared here for you. I know some people are writing this down, but here's a nice graph for you. And everybody's got a graph in front of them right now, so we can take an idea and we can calculate some values for this. And so we're going to take a look at this graph. Okay, so it is constant, absolutely. It's constant positive motion because each time interval it's going up an equal amount of distance. Let's just talk about this for a minute. Where does this thing, whatever it's moving, where does it start?
10 meters.
10 meters. Good. It starts at the 10-meter mark. And then it's going forward, going forward, going forward, going forward. So kind of a boring graph, but the thing's going forward at equal time up 1 over 1, but it's actually not up 1 over 1. Up 10 over 2.
Over 2. Over 2.
over 2. Yeah, so up 10 over 2. Or up 20 over 4. So either way, we end up with 5 meters per second. That's our average velocity. The slope on a dt graph, a slope on a position versus time graph, is going to be the average velocity. So you need to be able to do that. We can count it. Watch out for your units, because everybody's first inkling was to say up 1 over 1. So watch out for the intervals and be careful with that. You can also do it by formula, d1 minus d0 over t1 minus t0. So if I wanted to, I could do 40 minus 20, which is our change in position, over 6 minus 2, which is our change in time. You're always going to want to do later minus earlier. And rate of change, absolutely. Should have been, yeah, you should be seeing that in other classes as well. So 5 meters per second here. We've got to be careful though. Sometimes people have the false you can just divide distance by time. And that was great when you had just a couple of numbers, but you've got to be careful on the graphing. Yes.
Where'd you get the 40 and 20 and the 6 and 2 from?
Let's look at the ordered pairs here. This one is at 6, so this is our later time. So that would be our T1, and the position that goes with it is 40. And so the earlier time is at 2, and the position that goes with it is 20 for this particular point. So you can plug those in. We hit 5 meters per second. Be careful, though, not to think about it. And there is a homework question, and so you need to understand that if you just divide distance by time or position by time, you're going to get a wrong answer. So if I just used this ordered pair and did d over t, 40 divided by 6, I get 6.7. That's not the average velocity because it didn't start at 0. Same with here. If I took that ordered pair and did 20 divided by 10, that gives, 20 divided by 2, that gives 10. That's also not your average velocity. That's just a position. It's not a how far it went question.
But wouldn't the average velocity be 5 meters per second plus 10 meters?
No, you're confusing position with change in position. Because right here, it's just where it is at that time. It's not how far it's gone. Okay, because how far it's gone 20 meters in 4 seconds. But it started at 10. So if we even just look at this point 0, 10, it didn't go anywhere then. It just started there. And then 2 seconds later, it was at the 20 mark. So it's a change in thing, because if you're just looking at one individual time, this is, remember I said about the instant, that's at an instant of time where it is. It's not how far did it go during any kind of duration of time. And I want to relate it a little bit to that idea that I talked about earlier of limits once we start getting curvy graphs. But right now we just have this straight graph like this. All right. So since the average velocity equals slope, when the slope gets steeper, and we talked about this yesterday a little bit, when it gets steeper, then it means faster. When it gets more leveled out, that means slower on a DT graph. Once again, I've got questions here, but one thing we can say about a negative slope in terms of the speed, as the negative slope decreases, once again, as it gets steeper, the speed is faster. When it gets steeper, the speed is faster. And as it approaches 0, as it flattens out, it gets slower. And what does a slope of 0 mean on a DT graph? We talked about this earlier. Flat out. It's a straight line, but it's at rest. There we go. That's the word. So at rest. That means the position is not changing at all, even though time keeps going on. So the object is at rest. And those are some very key concepts for you guys to make sure that you are understanding. So slope of 0 means the object is at rest. Steeper means faster. Closer to 0 means slower. And then as it gets to 0, then it means that it's stopped altogether. So time can keep going. You can still have a straight line on a graph even when the object's at rest, because time keeps going even if something's just sitting there and not moving. Okay. And that's a super important thing to get your head around. Because you know that on the tests we have concepts, we have also problems, so you have to understand the whole package. I don't want you just understanding what the numbers are. I want you to understand what exactly these graphs are telling you. The better you understand how the graphs are working, then the better you're going to understand. Those of you that go to calculus, the better you're going to understand what's happening with the derivatives and the integrals and all those different things that are good with that. Okay. All right. I've got question. Yes.
If a line, if it goes up and it goes down,
Mm-hmm.
with that, when it's at the top point, is that at rest?
Well, let's think about that for a minute. He said if I have a DT graph, okay, so, and it goes up and then it goes down. Remember, it's position versus time, where it is compared to when it's there. So for something like this, it's starting here and it's going forward, and at this pointy point, it's turning around and going backwards. So at that instant, you can consider it having 0, but it's not for any duration of time. Okay, so it really, in this case, it instantaneously turns around and goes the other direction, which is really pretty much impossible. So something that would be a little bit more natural would be a graph that goes like this with a little bit of a curve to it. The math on that's a little bit harder though, and that's what calculus is for. Or if you went up and then you stopped suddenly and then you turned around, that would also be a little bit more natural than the quick turnaround, although we're going to do some problems with the instantaneous turnaround. So that actually was a very good question because it gives you a little bit of chance to talk about why it's important for calculus. So good question. All right. All right, so as long as velocity is constant, which is a straight line, this is like the third time I've said that. Position as long as velocity is constant on a DT graph, we're going to talk about what equation we can use for that. It's a super important question. We're going to relate this back to a straight line, which is mx plus b. Okay? Everyone should know about mx plus b. M is the slope, b is the y-intercept. But in physics, instead of mx, y, and x, we have position and we have time. So position equals slope times time plus b. This is our position time graph. This is b. All right? Where the object starts. It could be positive, or if it down here, it could be negative, but this is where the object starts. So it's the 0 position. Okay? Where it's located at 0 seconds. We call it D0.
So for B, because it has
So a 0 subscript tells you that this is my starting thing. So our starting location plus our slope, and our slope was representing what in a DT graph? Average starts with a V, velocity. The average velocity. So as long as V is constant, as long as it's not changing, as long as it's a straight line, you could just use the variable V to represent V bar. So what we can do is plug that in. In physics, rather than having mx plus b, they have b plus mx. You change over from one to the other, it's the exact same deal except for position, new position, equals the starting position plus the velocity times time. Way back in the day in algebra, you were always saying distance equals rate times time. That only works as long as the starting position is at 0. But when the starting position moves off of 0, then you have to take into account the starting position. This equation that we just found, okay, this equation only works if the velocity is constant. And I will bounce back for you to get a chance to write for a minute, but I do want to just finish this off with what we're explaining. We have a final position, we have a starting position, our velocity, and our time. This is the first of the equations that we're going to be using in order to solve problems. And that's where we're going to be going with this next. Notice I have this in giant big red letters. I have this in giant big red letters because it only works if velocity is constant. If it's not a straight line, if it has curves in it, if it's a parabola, or if it's any other type of shape, then we have to use other equations. So that's why we're going to look at and figure out where other equations come from. But this particular equation only works if velocity is constant. So it's a good equation. It's just a little bit dangerous. So we're going to be careful with it as we go. And very much emphasize that the velocity has to be constant in that. Okay.